All right, problem 2 is fairly self-explanatory, actually. We've got this, there's my pen, great. We've got this block being dropped from a height h onto the spring k. I guess the block is shaped like this to sort of show that, you know, it'll hit the thing and it won't slide off or whatever. Anyway, so it goes down, hits like that. We want to find the maximum distance the spring is compressed. So I'm just going to draw a little picture, sort of a sketchy sketch, of what the system is going to look like at the end. It's been compressed by some distance x, okay? So, and there's our little block there, more or less, with mass of m. And it's got a velocity of 0 here. It's also got a velocity of 0 at the beginning. It just dropped. And we want to find how far it compresses the spring at its maximum compression. So you can imagine it comes down, hits the spring, you know, it's going pretty fast, and it slows down, and when the spring is the maximum compression is the point where the block is stopped, because after that it's going to start to go back up, and then you get less compression. Okay, so assuming that's basically self-explanatory, let's label the important states of our system. So here's state 1, where it's just been dropped and it's not moving yet, but it's about to. And here's state 2, where it is now stopped on the spring. It's compressed it a bit. So for state 1, we've got potential energy, or sorry, kinetic energy. We've got potential energy due to gravity, right? And we've got potential energy in the spring. And then we've got E mech, which is the sum of all of those. And then for state 2, I'll do state 2 down here, we've got kinetic energy equals whatever, gravitational potential energy equals yada yada, and spring potential energy equals boom, and mechanical energy, which equals something. Okay, so let's just start it off. At the beginning, it is motionless, so kinetic energy is 0. Any object not moving, kinetic energy is 0. Easy peasy. Potential energy due to gravity. Well, this depends on where we set our gravitational potential energy to be 0. I'm going to say it's 0 right here at this line. I just happen to feel like that today. Okay, so potential energy of gravity is 0. You can set that point anywhere you want. You can set it on the ground here, although then you'd have to specify how tall this is at rest with like some, you know, let's call it like d, you know, but then that would all, your d's would all cancel out. So, you know, that's fine. You can just specify it anywhere because all that matters is the difference in potential energy between any 2 points or any 2 states of the system. Okay, so hopefully that's explained more than it's confused you. But anyway, I'm going to say gravitational potential energy is 0 here, which means that when it's this far up, when it's a distance, or when the block m is a height h above that, the potential energy there is mgh, and the total energy in the spring at that point is 0 because the spring is sitting there at rest. The spring has not been compressed or stretched or anything. 0. Okay, so mechanical energy at this point at this state is 0, 0 mgh. Okay. Kinetic energy at point 2, after this is already done its maximum compression, kinetic energy there is 0. It's stopped moving, right? Okay, gravitational potential. Now, this is where some people made mistakes. Gravitational potential energy is 0 when the block is at the rest position of the spring. But we're talking about after the block has compressed the spring a bit. So it's reached the 0 point, and it's gone down a little further by distance x. So potential energy at this point is negative mgx. And then potential energy in the spring is going to be, this is our spring potential energy equation, 1/2 kx squared for deflection of x for a known value of k. And so E mech there is going to be negative mgx plus 1/2 kx squared. So if energy is conserved, if we have no non-conservative forces acting, and I think we don't. Well, technically they don't tell you, but you basically assume that we don't, unless you're told otherwise. I mean, it has to be for us to solve the problem. Then we say these two are going to be equal. So that's going to mean if we set these two equal, we're going to have 1/2 kx squared. I'm rearranging things slightly, so I'm taking the bottom here. 1/2 kx squared minus mgx, and this is going to be equal to this, but instead what I'm going to do is go minus mgh equals 0. And now what we have is a quadratic in x. And this is going to be a little annoying to solve. So let's see if there's anything we can do to make this a little easier. I'm going to divide through by m and g. So to get both, yeah, I'm going to divide through, that's right, I'm going to divide through by m and g. So this is going to be k over 2mg times x squared minus x plus h equals 0. Okay, so for our quadratic formula then, capital A is k over 2mg, capital B is -1, and capital C is 1. So now let's see, x equals, so it's -b, so it's 1, plus or minus square root of b squared, which is 1, minus 4ac. So minus 4, in fact, you know what? I'm gonna keep capital A in there, and then C. Okay, all over 2A. I'm gonna leave the 2A in there. Okay, and so what I'm gonna do is I'm simply gonna use my calculator to calculate what A is, and then that'll be a little easier to solve. So coming over here, A is this k over 2mg, and for me that's going to be, let's see, k over 2mg. So okay, now this is where it gets tricky. K is 1960 newtons per meter. Okay, 1960 newtons per meter divided by 2 times m, which is 2.0 kilograms, times g, which is 9.81. Okay, so there's our, which is almost 50, 49.95. Okay, so A equals 49.95, and then x equals, so we just have to, like, you know, solve this obnoxious thing. Is that right? Wait a minute. B squared minus 4ac. That can't be right because, no, that can't be right. A, B squared minus 4ac. Oh, c isn't 1, c is h. That's I hope the answer. So it's 4a times h. Right, b squared minus 4ac. Okay, so now I think, oh, and this is negative. Wow, bad job, Mr. Smith. All right, so because this is a negative h here, minus 4ac positive, so this is actually plus. That's going to solve a lot of the problem. Okay, so let's see, x equals 49.95. So this is going to equal, if I, you know what, I'm just going to round this to 50. And that is going to mean x is going to equal 1 plus or minus square root of, so this is going to be, A is going to be 50 times h, oh, I'll make it 49.95, fine. So, 4 times previous answer, times, and then h I believe was 95 centimeters, let me check it. Yes, so 0.95 meters, and this is 1 plus, so square root of that, and then we get 1 plus, okay, all over 2 times A. So just making sure this is correct. Okay, negative, right, 1 plus or minus. Okay, I think that's right. So this should be my answer, which is 0.148 meters. So let's see if I did this right, or if I'm just going to fall flat on my face. And got it. All right. So there we go. So it's a bit messy because you have to solve for that quadratic. And some people, like I said, the common mistake that a lot of people made was forgetting that as it goes down after hitting the spring, there's still gravity doing work on it, which means you're still spending gravitational potential energy. So your gravitational potential energy is going down as you move. So people were basically saying this term equals 0. And if you did that, then it was equivalent to solving this equation with this term gone. And you get a very close answer to the correct one, but not quite. It was close enough that some people thought there must be like a rounding error from WebAssign, but no, it's because you forgot that you're slightly off.